Sairam and welcome to the next session. In this session, we will be taking a closer look at vectors. Let us begin this session with a prayer. Om Sai Ishwaraya Vidmahe Satya Devaya Dhimahi Tanna Sarva Prachodayat. Om Shanti Shanti Shanti. So given a vector, it has two aspects to it. One is its magnitude and the other is its direction. What do we mean by magnitude? Magnitude represents the length of the vector. Okay. And what is the direction? Direction is actually pointing to in a specific orientation, right? So how do we represent it physically? We represent this by an angle theta. Okay, so the length of this vector is represented as the magnitude, while the angle represents the direction. Okay, so given a vector A, let's say, let's write this components, which is say 5 and 2. Let's try and find out what is the magnitude of this A vector. How do we represent the magnitude? We represent it with this double lines. We need not keep putting this arrow above this alphabet. At some point we can stop it. We need to find the magnitude of this vector. Okay, how do we find it? Simple Pythagoras theorem. We project the vector down to the x-axis. In 2 dimensions we are trying to find first. And when we project this onto the x-axis, when we say project, what's the idea? Idea is like keeping a light source above, perpendicular to the direction of y. Perpendicular to the direction of x, and the rays of light are falling on this vector, and therefore the shadow will be reaching only till this point, right? So this is the projection of this vector phi 2 on the x-axis. Okay. Now we see that there is a right angle triangle here. Here is a right angle, and therefore we can use the Pythagoras theorem and then figure out what is the length of A, right? So we know that in the y direction we have moved up by 2 units, and in the x direction we have moved by 5 units, and therefore using Pythagoras theorem the length of A must come out as 5 square plus 2 square. So that will give us root of 29, right? Okay, this is good in the in 2 dimensions. What do we do in 3 dimensions? Now in 3 dimensions, what we are going to do is we are going to apply the same idea. So we have a vector here, say 5, 7, 3. Let's say we call it the B vector. So we can write B as a column vector here, saying its components. And let's use the same idea. So keep a light source above and let the rays of light fall on this vector, and the important thing is that the light is now perpendicular to the xz plane. Reason is we want to find the shadows, we want to find the shadow of this vector on the xz plane. So we take a light source that's perpendicular to this plane, right? So there is enough light source that's coming from here, and it falls on this vector and it creates a shadow, right? Now let's try and draw how this shadow look like. So one easy method to understand this is, if I have a B vector which is 5, 7, 3, how did we reach this vector? So one way to look at it is, I walked 5 steps on the x-axis, I moved 3 steps on the z-axis, and then moved up by 7 units in the positive y direction. So when we cast a shadow of this vector, it is effective in bringing the y down, right? As simple as that. Just pull this vector down in straight and push it, or just press it onto the xz plane, right? So and when we press it like that, we will find that this could be the shadow of it. This might be the shadow of it. Okay, but let's remember how we reached this point. We moved 5 steps, moved 3 steps in the z, and then moved up by 7 steps. Now the 7 steps up are gone, and therefore that leaves us with the 5 and the 3 here, which means that the shadow is going to have the coordinates as the y becoming 0, right? On the xz plane y is 0, it doesn't rise, 5 and 3, and therefore this vector, now let me call it the S vector standing for the shadow vector, is 5, 0, 3. So let me write this down here. S is 5, 0 and 3. Okay. Now the nice thing is, though this is a three-dimensional vector, one of the components of it is gone, and the concept that we used in 2 dimensions can be applied here, right? I'm not saying that this is equivalent to 2 dimensions. It is still 3 dimensions where the one of the dimensions is not or is nil, but the concept that we used here can be applied here, right? Let's see what is the concept. So here it is. I have 5 steps that we have moved in the x direction and 3 steps in the z direction, which means that we are talking about this being perpendicular, is it not? This is x and z, right? This is like 3 dimension coming out of the screen. Since this is perpendicular and we have the hypotenuse, we could apply the Pythagoras theorem, and therefore we can talk about the magnitude of the S vector, and we know this is going to be, this is 5 and this is 3, and therefore this will be 5 square plus 3 square and square root of it, right? So let's write this down. This is 25 plus 9, that's a root 34. Great. Now we have the length of S available with us. Now let's try and concentrate. How do we find the length of B vector, the magnitude of B vector? Okay. Since we have this and we go straight up from this point, 7 units, you have to visualize this in the 3 dimensions. One way to look at it is, the S vector is lying on the floor, right? The S vector is lying on the floor, whichever direction, doesn't matter. Keep imagine a vector on the floor. Now imagine a vertical stick that you place on the floor, right? You can easily make out whatever be the direction of the S vector, it will always be perpendicular to this vertical stick, is it not? Because the entire xz plane and this vertical stick are perpendicular to each other, and therefore, though in this diagram it's not very obvious, but the point we are trying to make is that this is also a right angle, right? This is also a right angle. Now we have S on one side, we have the magnitude of it. On the other hand, we have this 7 units, and therefore now we can use same Pythagoras theorem and calculate B now. Therefore, let's try and calculate the magnitude of B vector. So the magnitude of B vector is going to be root of S's magnitude squared, so that is basically root 34 whole square plus this is 7 units, and therefore that will be 7 square, so that will be root of 34 plus 49, right? So that is 83, if I'm right. Okay, so the magnitude of B vector must be root of 83. So let's look at one interesting fact here. If you see here, what has happened is we had a 5 square and 3 square, which is these 2 dimensions, 5 square and 3 square, and after that we have squared that and then again taken 7 square. Effectively looking at it, looking at all these two things, what we could actually write? We could write that the modulus of the magnitude of B vector is actually root of 5 square plus 3 square. Remember that we took the square root and again squared it here, which is effectively this only, 5 square and 3 square, plus the last one that we picked up is 7 square, right? Let's calculate this. So obviously this is going to come out to be the same. Sorry, let me write it a little clearly. This is 25 plus 9 plus 49, which is again be square root of 83, right? So what do we find? If we are looking at 3 dimensions, ultimately the Pythagoras theorem is leading us that the magnitude of the vector is nothing but sum of their squares and a square root above that, right? Now we could extend this same idea or this principle to n components, and let's write this down, that when we have a vector v with say n components in n dimension, what will be the magnitude of the v vector, right? So we can use the same principle and we can apply this and say I will get v1 square plus v2 square or so on till vn square, right? So we take each component, square them, add all the components and then take a square root, then I get the magnitude of the v vector, right? I hope that the magnitude part of the vector is quite clear. All that we are applying is one theorem called the Pythagoras theorem. Okay, now let's talk about direction of a vector. As we told earlier, we know that the direction is going to be represented by this angle called theta, right? Okay, there are a few important points to remember here. Generally, this angle theta is measured in the counterclockwise direction, right? When I say counterclockwise, so let me mark this. No, this is the direction from x-axis towards this way, opposite of the clock moving. And if you have a vector somewhere here, you can make out that you will still measure the angle in this direction. Similarly, when I have a vector here, I am going to still measure the angle like this, and if I have it here, still we are going to measure it in this fashion. Okay, now that is one way of measurement, right? You will always get non-negative angles for it. Okay, but there are times where you will notice that the angle could be given as minus 30 or say minus pi by 2. What is the meaning of it? All that we are talking about is, instead of the counterclockwise direction, if I move to the clockwise direction, right? So if I, instead of measuring it in the counterclockwise, let me try and measure it in the clockwise direction, right? You will find that we can represent the same vector, its direction, by another angle, right? And that time I am going to represent this as a with a minus sign, and that denotes that I am measuring it in the clockwise direction. So what does that tell us? In the counterclockwise, if I measure everything, then all the angles I'll get only non-negative. Whereas if I'm going to talk about clockwise for in this fashion for half of the r square, r2, and on the top half, if I'm going to use counterclockwise, then I'm going to get angles in the range of minus pi to pi. Okay, so let me draw another diagram and we will discuss a little more on this aspect of direction. Okay, so let's take two vectors. I have, let's say, a vector and the b vector. A is a 6-2 column vector. B is 3-5, another column vector. Did I write that carefully? Yes. Okay. As we said regarding the direction, it's going to be measured by the angle, right? So let's say that angle A subtends an angle of theta 1 with respect to positive x-axis, measured in counterclockwise direction, and B, let's say, is theta 2, right? Remember, the angle is from the vector to the x-axis, positive x-axis. We are measuring theta 1 and theta 2. Okay, so remember that this term called direction, of course, we are going to use the angle, is also looked at in another way called as slope. And I am sure you might remember, okay, here we are talking about theta. We may look at this sometime, right? We may look at what is called as tan theta, right? And I can probably look at this specific term here, and it may give us a better understanding, right? So let's talk about this tan theta for a while. Let's look at this this specific vector A. Okay, what it says is, when it moves 6 steps away, it rises by 2 steps, right? So here is a beautiful way to look at slope. We are saying when for vector A moved 6 steps on x-axis, and when it moved 6 steps on the x-axis, it rose, which means that we are talking about the y-axis, it rose by 2 units. Great. Now look at the B vector. It for a movement of 3 units on the x-axis, it rises by 5 units, right? Okay, so it is this kind of a ratio that we are very interested in, what can be denoted as rise by run. Now here is a very interesting way to look at it, and it is not in any way my idea, but I had understood this from Khan's Academy, and all credit goes to him for driving home this point. But it's a good way to look at slope. right? So what it says is, look at the proportion of when I run a few steps, right? So what we call as run is going to be on the x-axis. When I run a few steps, how much do I rise, right? And that proportion is going to help us understand the slope. Okay, so this specific vector says for 6 units I just rise 2 units up. Okay, the same, let's ask, if since you are saying that for 6 units you rise by 2 units, how much should have been risen when you just moved 3 units? So obviously when this vector probably would have moved 3 units, it would have risen only by 1 unit, is it not? And what it says is that this specific vector here, right, if we try to mark this vector and say that we call it the C vector, right? So if you want to talk about this C vector is going to be 3, 1, right? What do these two vectors, what do A and C vectors say? They're saying that for movement of 3 units on the x-axis, I will rise 1 unit. Whereas A is saying that for movement of 6 units, I rise 2 units. But essentially they're saying the same thing. And that is why the angle that is made by C vector or A vector is the same. Reason? The slope is the same. And how did we understand slope? Here it is, rise by run. Since slope is same, this value must be the same, and therefore theta must be the same, and therefore these two vectors are pointing in the same direction, right? Their slope is the same. Okay, what is different between A and C? They differ only in their magnitude, right? If you take a scalar multiple of this, you multiply this by 2, then you get this A vector, as simple as that, right? Let's now look at the B vector. The B vector says that for movement of 3 units on the x-axis, I'm going to rise by 5 units. Okay, then in the same line, right? So let's try and extend this and then say that since for 3 you rose to 5, when I move 6, how much will you rise, right? So it's going to rise to 10 units, right? So which means that at this point, let's say that we call this the D vector. The D vector, this is going to be 6, 10, right? If you talk about the D vector, which is 6, 10, whereas you have the B vector, which is 3, 5, right? What do we get? That these two must be equivalent, because both of them are saying the same fact, saying that for the movement of 6 units I rise 10, or in a sense if I move 3 units I'm going to rise only by 5, right? So that means that these two are in the same direction. What is the difference? The difference between D and B is only in their magnitude. Again, pick up the scalar 2, multiply it here, you will get it here. Okay, so this gives us a rough idea of what is direction, and that it is very well related to slope, right? That is why we spent a few minutes on this concept. Okay, so with this idea of vector direction and magnitude, let us proceed to the next topic, where we are going to discuss what are called as unit vectors. Unit vectors are a very simple definition. Any vector whose magnitude is said to be 1 is termed as a unit vector, right? So let's take some examples. The simplest example can be, if we take a vector 1, 0, the magnitude of this vector is 1, or if we take 0, 1, the magnitude of this vector is 1, right? One common mistake that we tend to do is, we sometimes may pick up this vector 1, 1 and may sometimes mistake it to have the unit vector, but that's not unit vector, right? If you let's find the magnitude of this vector. Magnitude of this vector will be 1 square plus 1 square, which is actually root 2, right? Okay. But given any vector, right? So if we are given any vector, let's say that we are given this vector, is it possible to find the unit vector in this direction? So here also we can ask, since this is not a unit vector, can we find the unit vector in the same direction? Now what is the knowledge that's going to help us? Just now we have understood the concepts of magnitude and direction, right? We clearly understand when we say we want the unit vector in the same direction, which means that it must have the same slope, right? So you see here that when I run one step, I would like to rise one step, right? So that's the kind of the slope we are looking at. At the same time, we want its magnitude to be 1, right? So with this understanding, let's ask now, how do we do this? So since we know that the magnitude of this vector is root 2, let us simply divide this vector by root 2. That's it. But then we don't know what is called division. What we essentially saying is that do a scalar multiplication of by the inverse of the magnitude, right? So 1 by root 2 scalar multiply this with the vector, and we know now what will be the output. So let me call it u. So we multiply each of those components, and therefore this will be 1 by root 2 and 1 by root 2. Now you can calculate the magnitude of this vector, that will be actually 1. So you can calculate this. But what is interesting is you can see the slope of this vector, right? So for moving this much, or running this much, I rise this much, which means that the slope is exactly same as this, which means we found a unit vector in the direction of 1, 1. Fantastic. Similarly, if you are given any general vector like this, what do we write for that? So unit vector u in the direction of v is going to be 1 by root of x square plus y square, and we do a scalar multiply of the original v vector. This is my unit vector in the direction of v. Another way to handle unit vectors or find unit vectors is to look at what is called as the unit circle, right? So with a radius of 1 at the origin, if we have a circle, then any vector which is touching that unit circle has got to be a unit vector, simply because the radius of the circle is 1, right? So when we look at the unit circle, we can also look at this kind of a format for unit vectors. So pick up any theta and fill this up. Any cos theta sin theta pair will always form a unit vector, right? Reason is because we find that root of cos square theta plus sin square theta, for any theta this is going to be 1, right? And therefore this will always form a unit vector. So now that we have an idea of vector, magnitude, direction and unit vectors, let's move to something more interesting. Okay, so here we see that we have two vectors a and b, and let's say that we are now interested in asking, here it is, let me just write this down. We are interested in length of the shadow of a vector on b vector, right? So it's a very important statement you're looking at. We are suddenly interested in finding, see, we know how to find the magnitude of a vector or b vector, we know how to find their direction, okay. What we're interested now is, we are interested in finding the length of not a but its shadow that is cast on b, okay. In this case, we have picked up the b, which is very simple b, because it's in the direction of in the direction of x-axis. Is it possible to find the length of this shadow? Okay, so what are we going to do? We are going to assume rays of light in this direction, let's say, and the shadow is cast. I mean, we have a fair idea of this concept. And what is going to happen is, as the shadow falls, it's a perpendicular projection here. It's pretty easy to identify this point, is it not? Right? We are saying this is 3, 4. 3, 4 means that I have moved 3 steps here, and 4 I have risen up in the y direction. But since the shadow is going to fall flat on the x-axis, this point is simple. It's going to be a 3, 0, right? Okay. And we are looking at what's the length of that, right? So it's pretty easy to understand it. The length of this is going to be simply 3, nothing more to it. But we want to talk about this using the direction concept as well, which means that if we mark this angle to be theta, we would like to know what is this part, what is the shadow part. So let me call this as, say, S is the shadow, right? So B is the vector in yellow, which is still 4, 0. S is that smaller part, the 3, 0 vector, but we want to find S in generic terms, right? We are not worried only about the example 3, 4. We want to find it for any A that is having a direction theta. Okay, so it's pretty simple, using trigonometry. Let's ask ourselves if this is theta. Okay, here is a right angle here. Therefore, what could be cos theta? Right? Cos theta will be adjacent by hypotenuse. So I can write here cos theta is actually S by A. Right? So when I write like this, I should be careful. It should be the magnitude of the S vector by the magnitude of A vector. Right? Or if you want the length of the shadow, it is simple. You give me the vector, I can always find the magnitude. Given the vector, I can find the magnitude, and let's say the direction is given for now. All that I need is simply use cos theta and I have got the length of the shadow. Now, when we look at this length of the shadow, it actually hardly matters, it really doesn't depend on the B vector as such, right? We could say that it depends on theta, and theta is actually the measure of the angle from the x-axis to A, which in essence is going to be the same from B vector to A. Okay, let's try and generalize this, right? So instead of calling, as B vector or X or whatever, we will say, you give me some B vector from where I measure the angle theta. Instead of the B vector, why don't we look at the unit vector in the direction of B? Right, so this is what I'm going to write. If theta is the angle between A and B vector, what will be the angle? What will be the angle between A vector and the unit vector? The unit vector in the direction of B vector, right? See this angle between A and B vector is theta. Okay, and we are finding the unit vector in the direction of B. Now you understand this statement because we just now completed what is unit vector. Therefore, the angle between A and the unit vector in the direction of B has got to be the same. So this will also be theta. Okay. So this is how we are trying to generalize it, right? So given A and B vectors, we will be able to give the length of the shadow of A on the unit vector in the direction of B, and that will be the magnitude of A cos theta. So let's call this unit vector in the direction of B to be, say, some u vector. Let's say we call this as the u vector. Okay. Now people are quite interested in the length of the shadow, basically because we are going to use this concept called as projection many times, right? And that is why there is a keen interest in the length of the shadow, because it's projection, right? And that is why this has got a definition in vector algebra, and this is defined, this part, magnitude of A times cos theta, has got a definition, right? This has been defined as A dot u, right? You know what is A vector. A vector is given to us. U is the unit vector in the direction of B vector. This is a definition, right? So this is called a dot product. A dot product is a scalar definition, right? This is it involves two vectors, but its output is a scalar. It's a number, a real number. So we pick up these two vectors and then bring up a scalar. What does that represent? It represents the length of the shadow of one vector on the other vector. Okay. Now, if you want to further generalize it, right? We know that u is the unit vector in the direction of B, and just up here we saw what are unit vectors. So instead of writing it like this, now I can write it as A dot B divided by modulus of the magnitude of b, right? So we can also write it like this and say that this must be equal to a cos theta. But since the dot product is only between vectors, we can bring the scalar out and take it to the other side, and therefore they come up with this definition which looks quite decent and symmetric, and this is called as the dot product of two vectors. So given any two vectors, a dot product of them is defined as the product of their magnitudes times the cosine of the angle between them, right? So we may think that this kind of a definition works only when b is in the direction of x, or we have taken it aligned with the axis. Not really so. So we can pick up another example right here, and we will see how this works. So let me pick up another vector. I've drawn another vector in orange. So let's say that this vector is 4, 2, and let's ask this question: what if this is the let me give it some name. Let's say this is the c vector, and we're asking how do I look at a dot c, right? How do I look at it? Because the definition is going to be the same, so I'm going to write here the product of their magnitudes times cos theta, but this theta this time is not this theta, it is this, which means that if I call this as theta 1, let me better put it here as cos theta 1, where theta 1 is the angle between a and c. How does that work? Okay, what we do is, remember when b was in the direction of x, it was very easy to drop the perpendicular. Okay, now if we want the shadow of a on c, what we need to do is we have to imagine rays of light perpendicular on c, right, like this, right? So let me draw the perpendicular carefully. So in this direction, so we have rays of light hitting perpendicular on a at c, and we find that the shadow of a will be cast on this c, right? So let me just try and project this. Okay, so it may fall somewhere. Now we can even extend this vector how much ever we want. Sometimes if the unit vector in this direction is smaller, of course we know that it will only touch the unit circle here, so we can extend that and then meet it, and that will be the length of the shadow, right? And you see that there is a right angle triangle again forming here, right? So look at this triangle here, and we know that this is a this is the shadow part. This is the shadow length is going to be s, and this is a theta 1. Apply the same trigonometric rule and we will get the same thing. So our formula still remains the same, right? Now interesting question is going to be, what happens to the length of the shadow as the base moves closer to a, right? Initially we had this b vector on which I had the shadow. It looked a little small to me. Now when I move a little closer, when I move my base a little closer and then cast the light, now it appears a little longer to me, right? Okay, let's go as close as possible. What will happen if I ask for the length of the shadow of a on a itself? Right, of course we will still say that I am going to give the shadow length on the unit vector. Okay, but the direction is going to be the same. But the point here is that what will be the length of the shadow? The length of the shadow has got to be the same as the magnitude of a. Let's ask, is that correct? Let's try. We are saying this is my length of the shadow, and we know you give me any vector, this is what it's going to be, where theta is the angle between a and the b vector, or the unit vector in the direction of b. Now what's our b in this case? A itself. Therefore what is theta? There is no angle, which means it's 0. And what is cos 0? It's 1, which means that this is going to be a. The length of the shadow matches the magnitude of the original vector, right? So this is the concept behind what is called as the dot product, and in the next session we will be dwelling a little more deeply about dot products. Right? So let us end this session with a prayer. Om Shanti Shanti Shanti.